Welcome, everybody. I am Johan Ferreira. I'm sitting over here in the boardroom. We are at meeting you live from the University of Pretoria. And I'm very happy to introduce you to Azam. And she is one of our excellent postdoctoral fellows, Dr. Kheyri, and she's at the Department of Statistics at the University of Pretoria. She obtained her PhD in statistics from the renowned Firdausi University of Mashhad in Iran, and then she joined the Department of Statistics here as a postdoctoral researcher in November of 2021. Her research interests include undirected graphical and network modeling and high-dimensional data analysis. The talk today focuses on a new Sparse estimator for high-dimensional precision matrix estimation. Thank you, Azam.
Thank you so much. Thank you for your kind introduction and also your support and the opportunity to present today. Thank you so much for everyone to join us today. Good morning, everyone. I have to say first, good morning, everyone. And thank you joining us for this seminar. I'm going to talk about our research, new sparse estimation for high dimension precision matrix estimation. And I like to start with you can see a structure of my presentation. I can divide my presentation to different parts. The first part, I'm going to talk about the definition of graphical model and the two main classes here. And we're going to talk a little bit more information about graphical model and relation between these two classes. And after that, in second part, I'm going to talk about our proposed method to solving the estimation of precision matrix in high dimension case through the graphical model. Sorry, can I find this one because I can see look at I think full screen, but yeah, it's fine. Okay, sorry. As a definition for graphical model, it's a probabilistic model that captures the statistical dependency between random variables for us and do this as a network. So if you ask me what's the application of these two, I can say that anywhere, any field that you want to model interaction between random variables, it means that you need graphical model. And as some example, I can say that natural sciences, social sciences, economics, etc. We can use all of these. We can use graphical model during these sciences. And we can divide the graphical model to different main class, actually undirected graphical model and directed graphical model. As you can see, I have two examples for both of them. And this is the weather forecasting for about some city in South Africa. And this one is a gene regularity network. And as you can see, here we have a directed graphical model, and the left side we have undirected graphical model. And it's the data can tell us which one of these graphical model we can use. In undirected graphical model, we just talk about partial correlation, but in directed graphical model, we talk about causality. It's not just the interaction between random variables. So if you ask about motivation, I can say that these tools give us a representation about joint distribution with respect to some local relation between random variables. And what about the start point for using graph to represent the interaction between random variables? We can actually mention three different communities here: statistical physics, genetics, and also statistics. And what about the graphical model that these days I know it's actually a combination of graphic theory and probability theory, and it's a powerful tool give us this opportunity to model multivariate data. And in this slide, I'm going to show you the different information that we can actually find from the directed and also indirected graph. The left side, you see the directed graph, and we can factorize the relation between random variables with this equation. And this is actually, we use this concept that we have to use this actually for every random variables. We have parents, for example, with this direct age. A is a parent of C and C is a child for A. So we have to consider every random variable given parent. So we can factorize the joint distribution like this. But what about this one? How can I don't know how we can be ranking. I don't know. I can do something. You know something. I can do that.
The rest of the audience can see the entire slide.
Okay, so it's fine. I'm the only that. Okay, I can see. Okay, for undirected one, you can see that we can represent the joint distribution with respect to some potential function. And every age here show us a potential function, for example, for this one between A and C, and for this one between B and C. And this is a clicks here. We have a definition for that in graph theory. What is the clicks? It's a subgraph of the main graph that every nodes are connected to each other. It's the definition of clicks. So we can factorize the joint distribution with respect to these potential clicks and write this. So you can see the different information that we can actually find from these two different kind of graphical model. This is one clicks, and this is another one, and this is the last clicks for this graph. What about Bayesian networks? We're going to talk a little bit more about Bayesian networks. There is a famous property for Bayesian network being a cyclic. We're going to talk about it. It means that there is no structure similar to this in Bayesian network. It doesn't make sense. And we're going to show you that it's not possible to have something like this. The joint distribution between random variables can rewrite and factorize as follows. And you know that we can write this, and also we can write this. It doesn't make sense, but it's correct, even just the only time that we have the all probability equal to 1. So in the general, we can say that it's not valid situation for Bayesian network. So we can call Bayesian network also directed a cyclic graph. And what about the dependency between the nodes in this kind of graph? The first rule is that each variable is conditionally independent of its non-descendants given its parents. Let me show you. Consider this as a variable, and A is a parent of C. And what about the non-descendants? B and D are non-descendants. So we can say that C independent of B and D given A. As another rule, we know that each variable is conditionally independent of any other variable given its Markov blanket. What's the Markov blanket here? Let me show you. If again we consider a random variable C, A is parent, E is a child, and also D is a child parent. We call this set as a Markov blanket. So we can say that C is independent of B given these random variables. So it's the information that we can understand from Bayesian network. What about Markov random field? In Markov random field, if we consider two disjoint set of random variables S and T, we can say that they are conditionally independent given a separating subset. What's the separating subset? If we consider all paths between S and T must travel, this path must travel through the separating subsets. Let me show you an example. Consider A as a S and C as a T. And what about the path between A and C? We have these paths, and also we have another path like this. So we have two different paths to start from S and end to C. And what about the separating subset? This one can be a separating subset, this one can be a separating subset, and also this one can be a separating subset. So we can say that A and C are independent to each other given every of these subsets. As a conclusion, I can say that any two non-adjacent variables are conditionally independent in this graph. And also, we can say that any variable is conditionally independent of other variables given its neighbor. And the collection of its neighbor we can also call Markov blanket, again in the framework of Markov random fields. An important question is that are Bayesian networks Markov random fields or not? We're going to talk about the relation between two main classes actually. If you want to answer this question, we start with a simple example, just two variables and one edge between them. You know that we can factorize the joint distribution for the first part for the Bayesian network as follows, and we have just this expression as a potential function between A and B for the second graph. If we consider and define this potential function as the above equation, so we can say that it can convert Bayesian networks to Markov random fields. So it's easy. But if we want to add some other variables to this situation called chain, we have three random variables and this kind of situation for a graph. What about the chain? Again, we can represent the joint distribution with respect to every of these two graphs as follows. And you can see that I show that we can consider it's just one option. It's not unique. We can factorize, we can consider these two potential functions as follow, and then we can again convert the Bayesian network to Markov random fields for this situation. What about shape parents? If we consider this situation, we can represent the joint distribution as follow, and again you can see that I have the option to choose the potential function and find the relation between them. So shape parents also easy. What about shape chart? If you consider this one, you can see that we can represent again joint distribution like this. What's the result problem here? As you know, in the first graph, A and B are dependent given C. But in the second one, A and B are independent given C. So it's our problem here, and we cannot convert the Bayesian networks to Markov random fields here. We can solve this problem with adding an edge between these two parents, actually. So now A and B are not independent given C, and we have to add edge between them. So if you want to converting Bayesian network to Markov random fields, it means that we need to normalize our co-parents together and lose marginal independence of parents. So if I ask again this question, are Bayesian networks Markov random fields? You will say that no, and also Markov random fields are not Bayesian networks. So we have this situation for directed graphical model and undirected graphical model. So it's the it was for the as an introduction for graphical model, what is exactly graphical model and what's the undirected graphical model and directed graphical model and the relation between them. So we can start the next part of my presentation talking about our research. What's the purpose of this research? It's a general purpose. We're going to extract the information from data and find a model for data. And the question is that how we can do this? And the answer is that with network inference, we can find a graphical model that shows us the interaction between random variables in a system. So we want to use graphical model to solve a problem. As any other problem solving, we have to consider assumption to rephrase our problem and can solve it. As a main assumption, we consider here that data comes from a multivariate normal distribution. So I can say that we are focused on Gaussian graphical model. In Gaussian graphical model, we consider it to one pair. X is a random variable that comes from a normal distribution here, p-variate distribution, and a graph. And graph are actually related with covariance matrix of these random variables. And good property that we have in Gaussian graphical model is the reason that we consider this assumption here. There are a relation between sparsity and being independent, actually independency between random variables. Let me show you with an example. So we have a relation between sparsity and conditionally independence. If we have, for example, 8 random variables and we have this graph and this relation between them, it means that if you cannot see any age between x2 and x3, it means that you have to find a 0 here exactly in x2 and x3. You have to find a 0 in precision matrix. Precision matrix is the inverse of covariance matrix. So instead of finding that graph, we try to estimate the precision matrix in this framework. One common way to estimate the precision matrix is using the maximum likelihood estimator. If we consider a log likelihood function and try to find a solution for this optimization problem, we can find the inverse of sample covariance matrix as a solution for this. But we have 2 issues here. The first one is in high dimension case, we know that S is as a sample covariance matrix, it's not invertible, so we cannot find the estimation for precision matrix in this way. And also, we are interested to find some sparse solution for precision matrix. So if we can actually, even we can consider the inverse of covariance, sample covariance matrix as an estimation, it's not actually interesting for us because we try to find those variables that are independent given random variables. So we are looking for finding a 0 in precision matrix. For solving these 2 issues, or one common way is using regularization. In this method, we add a penalty to log likelihood function and try to solve this new optimization problem. And for example, the famous one is G-lasso that they use L1 penalty. Yeah, they use L1 penalty that the solution of the G-lasso is a sparse solution. And we can control the sparsity with this tuning parameter here. And the question here is that if I don't want to have a sparse solution, what we can do in high dimension case? We can consider another penalty like a Frobenius norm penalty. You can see a general form of ridge estimator and some other documents that rule. You can see the definition of general case of ridge here. They use a Frobenius norm. And also T here is a target matrix. It means that we have a prior knowledge about the precision matrix and we want to shearing cage the estimator, difference between estimator and that target matrix here. So we can use this. And what about our proposed method? We want to consider a combination of these 2 estimator. add a sparsity to model, and also add this add the advantages of using a Frobenius norm in model, and also add the information, prior information like target matrix to model. For solving this kind of optimization, we have to, at first, we have to consider a derivative of the equation and consider this, we say normal equation, consider it's equal to 0 and try to solve it. And I don't want to explain every equation here, but I want to show you the structure of how we can try to solve this kind of problem. For solving the problem number 1, we have to consider this structure. You know, we have to update every row and column in a one step. And in every step, we consider just that row and column as a variable and rest of elements fixed. So we can update this row and column for every step and go for another row and column and repeat it until convergence. So it's the structure that we try to find a solution for the equation number 1. So for using this structure, we need to partition all of the matrices in equation number 1 as follows. And here we consider W as a covariance matrix, and you know that it's the inverse of preci-sion matrix. So we can kind of find the relation between the elements of these two matrices with respect to each other, and rewrite equation number 1 just for one column, and then try to change this and simplify this equation to a familiar one. And we try this and we find the equation number 6, and we know that it's a normal equation for this optimization problem. It's a famous optimization problem, and we know the answer for this, and so we can update every element of the matrix here for every step. So I can summarize everything in the algorithm number 1. We need to initialize preci-sion matrix and covariance matrix at first as follow, and then repeat the structure in the stage number 2 for every row and column until convergence. So we use the previous equation and update every element step by step, and use that updated element to update another element in another row and column. So it's the structure of that we can do to find our estimator here. Also, we consider another scenario, G-lasso scenario. In G-lasso scenario, W is not exactly inverse of preci-sion matrix. We have another relation between them, and we try to use that relation and rewrite the normal equation and try to find a familiar normal equation for another actually optimization problem and answer our question. And now we can find the update for every element of the matrices, and then we can present everything in algorithm number 2 according to G-lasso. Again, we can initialize preci-sion matrix and covariance matrix as follow. And in every step, we can update the elements of partition matrix as follows. So it's the end slide about how we can solve this problem and how we can find our estimator. Now we're going to talk about the result based on simulation study. We consider different situation for our simulation study and consider sample size equal to 50 and 3 different dimension for P. You can see we try to consider also high dimension case for 100. And because we was actually interested to consider different kind of situation, we consider a 6 different network. First, the number 1 is a structure and non-sparse. Second one is unstructured and sparse. And these 2 are an unstructured and non-sparse. And the rest of them is the structure and sparse. And for comparing this strategy with GLasso, Reach, and GLNet, we consider a 100 independent simulation, and also we consider target matrix equal to 0, equal to identity, and also scalar matrix. And we find the optimal tuning parameter during the simulation with using the 5-fold cross-validation. And what about the performance measure? We consider 4 different kind of loss function as a performance measure. You can see here the result for comparing our proposed method to GLasso, Reach, and graphical elasticnet. And the 3 last estimator, the first one is our estimator when we consider a target matrix equal to 0. The second one when we consider a target matrix equal to identity matrix. And the last one is when we consider a target matrix as a scalar matrix. We can see the result also for L2 loss function and quadratic loss function, and also a spectral norm loss function. And in some case, we cannot find one winner for every of these performance measure. You know that we cannot find the estimator that works any situation better than others, but we can consider our proposed estimator as a good option for high dimension case. If I wanted to summarize the result, the first one, I can say that it's a good idea to consider a target matrix in the optimization problem, because you can see that it can improve the results. And the second one, we can consider our proposed estimator as a good option for in high dimension case for estimation of preci-sion matrix in Gaussian graphical model. And the last one is that we cannot answer the question that which kind of target matrix is good here. But according to our results, we can say that the identity target matrix works well here. And as a real data, we consider a 32 different currency for 4 years between 2018 to 2021, and try to find a network for every year and also for the whole these 4 years for the exchange market. This is the 34 currency that we use, and I try to summarize everything here. We actually, at first, I collect the data with respect to dollar as a numerator, and then consider and calculation all of these exchange rate with respect to all enumerate, all currency as a numerator, and then compute the daily log return. You know that we did this step because we need the assumption that multivariate normal it was an assumption. So we have to guarantee that, okay, we want to use this as a data that we know that it can be a multivariate normal. So we consider a daily logarithmic return, and then try to find a network with respect to our proposed estimator. As you can see, I try to represent just the 50 strongest relation between these currencies. You can see the result for 2018, result for 2019, and result for 2020, and also for the last year, 2021. And we try to find a network for all this period of time. And this is the result. And as you know, this age we can show us, and we can give us information about the exchange market network here. And I don't want to explain everything here, but you know that we can find a lot of information from this kind of graph. And if I want to summarize everything in one slide, we proposed a method to add the L1 penalty as add a sparsity to network, and also try to shearing cage the estimator to a non-random target value. And then we we find the two different algorithms to how we can solve this problem, and then simulation study. Then we try to show that it's a good option in high dimension case where you are looking for finding the estimation for preci-sion matrix, and also we use our proposed method for finding a network for real data. And this is the main references that I use for this presentation. And thank you so much for attention.
Thank you, Azam. I hope seemed occasionally there was some uncertainty with sound, but I checked in with some people that I could see it online, and they all told me they could hear just fine. So if you couldn't hear, my apologies. It was not intentional, at least I think. Do we have any questions? Any questions? If someone doesn't raise their hand, then I will pick someone from the online audience first.
Thank you for the online.
And then I move to the in-person audience. Oh, Jason is asking, what is a potential function?
Okay, thank you for your question, Jason. You know, we don't know what kind of relation there is, but you know, we know that we can factorize the joint distribution with respect to function just about, for example, A and B random variables, you know. Actually, graphical model in undirected graphical model help us to understand about the joint distribution function with respect to some local relation between random variables. We don't know exact what kind of function there is between, for example, random variables X and Y. But we know that we can factorize the joint distribution with respect to some potential function.
Anyone else with a question or a thought or a theory? Gopika said excellent. I also think it was excellent.
Thank you.
For those of you joining online, the in-person audience is going absolutely wild. There's applause and I have a question. I do hope I'm not revealing my ignorance. Sometimes I'm no expert in graph theory. I'm not like you. This idea of sparsity, I don't know how much you've thought or encountered when you think about sample size. And when you draw in, it sometimes reminds me of that age-old tale of, you know, when your N increases a lot, your T statistic in the usual null hypothesis testing will tend to be always rejected.
Mm.
So have you experienced something similar when working with something like the likelihood, when if the graph gets very large, that there might be obviously more and more points of sparsity, or where paths do not exist between different nodes, and how this kind of estimation technique would be able to account or think about that or not?
Your question is about when we are looking for talking about large P or large N.
Yeah,
large
N.
N?
Yeah.
It's not our problem, I think.
Then it's large P. Then
Okay, so you are talking about high dimension case.
Yes.
Yes. In high dimension case, yeah, we use the regularization method, but some people don't like it because they said that it doesn't make sense. We add some penalty to look like the function, and then you know we want to find the solution for this optimization problem. Why you can be actually sure that it's a good idea for this, you know, but it depends on the penalty. We choose the penalty in a way that force the solution into some structure that we know that it's a good structure. You know, we need some knowledge. I think we need some prior knowledge for this. For example, if you add the L1 penalty, it's not okay because we have a package for that. Okay, I add the L1 penalty. No, but add the L1 penalty, then I know that there are a lot of weak dependency between them. So I can have a sparse solution. So I add this penalty to this. But if I know that, okay, there we can find a lot of strong dependency between them, maybe there is some multi-collinearity between them. So it's better than we use, for example, Frobenius map for that. So I think the data talk with us and tell us what kind of graphical model is useful for that and what kind of, for example, penalty we can use and then solve the problem.
Thank you. One more question about how often do you rely on the assumption, or do you always work from the assumption of normality?
Okay.
I suppose in this high-dimensional case, working with Gaussianity, let me not answer the question with my opinion. Let's ask the expert their opinion.
I'm not, but I'm trying to answer this. Thank you so much, Siti, for asking this question. We have a lot of papers in different situations. It's not about a Gaussian graphical model. It's the start point for solving this problem, because you know, when we cannot do anything, just we consider, okay, it's a normal distribution, and then solve the problem. We have some papers on skewed Gaussian graphical model and some papers on using copula for that. And so they try to actually delete this assumption and find a general solution for this. So it's not only way that we can talk about graphical model.
One more in-person question over here.
My question is about the application, the examples that you mentioned. I want to know about the interpretation of that networks, about the currencies. What are the findings?
Okay. I told at first about, I don't know.
And so a lot of time.
Yeah, let me just explain to you. Yeah. At the first, I tried to show that what kind of information I can find from a simple network when we have an undirected graph. It's exactly the same of that simple example. You know, I show that if we have an edge between A and B, it means that these two random variables are dependent to each other. If there is no edge, it means that these two random variables are independent, even the rest of them. And we can talk about partial correlation, okay? If in the currency you find a relation between them, or you cannot find, we are talking about partial correlation. So I estimated actual partial correlation that networks for you, according to this graph. I can answer your question.
You can refer to the fact that there's a lot of information.
Yeah, there is a paper for that, and they try to estimate the partial correlation. And we use these tools, okay, graphical model to estimate the partial correlation. They use another method to estimate.
No, I wanted to see, for example, there is an edge between dollars and euros.
Yeah,
What is the meaning of it?
yeah, it can show us the relation between them, yes, and also the how much it's I think it's stronger.
That is
the other relation.
We can talk about that. Because it's
us, yeah, we can talk.
Okay, thank you everyone for your participation, but of course, thank you to Azam for an insightful and a somewhat discussive topic today. I think that brings us to the end of today's seminar, unless somebody else wants to raise a point. And I believe the recording will be available at some point from the CoE. Thank you, everybody. Have a fantastic rest of your working Friday.